Hello folks, we will be continue on Newton's laws. We'll be starting the applications of Newton's laws in chapter 3 soon. Before we move on to there, I want to talk about different forces we have in nature so we can understand the applications better. We are actually using applications at a simple format, so we're solving simpler questions now, and we'll move on to more questions, more complicated questions. And for that, we will need to know how to define forces, their directions, and how to find them. So I'm going to call this section Forces of Nature. And the first one we're going to talk about is gravitational force. So between two masses, there's always a force attracting each other. This is called gravitational force. This force is not very much felt in between two regular objects on the world. For example, in between two tables and chairs, or two human beings. It's still there, but small. It's generally felt when there are very large masses like the Earth and the Sun and the Moon. And this is the reason why we have solar system. These masses are all attracted to each other, attracted to the Sun. They are rotating around each other, maintain a balance with mostly the effect of gravitational force. So if there are two masses, M1 and M2, let's say, and the distance in between their centers is R. I'm going to use small letter r, sometimes it's capital letters, sometimes masses are in capital letters. I prefer to use small letters. But be aware again that there are other ways of usage for mass and distance in between these two masses. So these two masses, M1 and M2, will be always attracting each other. M1 will be pulling M2 with F1. And M2 will be pulling M1 with F2. These forces are equal to each other and opposite in direction, just like action-reaction forces. But they're not action-reaction forces, they are gravitational forces. So we will say F1 is equal to F2 is equal to F. Let me put my vector sign. Force is always a vector, and this is the gravitational force. Or gravitational attraction force. This force in between these two masses, F, in magnitude, is equal to G, a constant, times M1 times M2 divided by R squared, the square of distance in between them. So this is a force. This equation, this attraction is also called Newton's universal gravitational law, or Newton's law of universal gravitation. Also, so if you hear about Newton's law of universal gravitation, it is this: the forces attracting each other in between two masses. For Newton's law of universal gravitation, this is a force. The unit in MKS system is again Newton. Newton is equal to kilogram meters per second squared always. So in MKS units, we'll be taking distance in meters and masses in kilograms. G is a constant which is called universal gravitational constant, and it is equal to 6.67 times 10 to minus 11 Newton meters squared divided by kilograms squared. So as we are solving for gravitational force in between two objects, this is the constant we need to use. When we use all the MKS units, what we're going to be ending up with as a force will be Newton. That's it. Let's let's now do some examples. So I'm gonna read this again. And let's find the gravitational force, attraction force in between the Earth and the Moon. Let's see how large it is. Example 1, let's say. And let me find my example. So the Earth and the Moon, we know that the Moon is rotating around the Earth. It's smaller, there's a distance in between. I'm going to call the mass of the Earth M Earth, and mass of the Moon M Moon, so M, and the distance in between them R. So if the mass of the Moon is 7.35 times 10 to 22 kilogram, so mass of the Moon is equal to 7.35 times 10 to 22 kilograms. And the mass of the Earth is 5.98 10 to 24 kilograms. So M Earth is equal to 5.28 10 to 24 kilogram. 5.98, sorry. And the distance between them is 3.8 times 10 to 8 meters. So R is equal to 3.8 times 10 to 8 meters. What is the gravitational force in between the Earth and the Moon? So the question is asking, what is the force applied on the Moon by Earth or on the Earth by Moon, which is all the same force, so I'm going to call them all F and F. They're equal to each other, opposite in direction. I'm only talking about magnitude here. They're pulling each other, which is why the Moon is always rotating around the Earth due to the gravitational attraction. Now we are omitting the other effects from the Sun, other planets is also in there. This is all a balance that we need to look at, but we are only interested in here. What is the force in between the Earth and the Moon only? So we're going to use our general Newton's gravitational law of universal gravitational law is equal to G m1 m2 divided by r squared. G is a constant here again. M1 is M Earth. Let me put it. M2 is M Moon. I'll put M Moon divided by r squared. Now all I need to do is to enter the enter the values in MKS units, and the force I'm going to find will be in Newton. So I'll have to make sure my units are in MKS units, and they are already in MKS units, so we are good there. G is equal to 6.67 times 10 to minus 11 Newton meter squared divided by kilogram squared. So I put that number. My M Earth is 5.98, let me put a parenthesis, 5.98 times 10 to 24 kilogram. My M Moon is 7.35 times 10 to 22 kilogram. And the distance in between these two masses, these two objects, is 3.8 times 10 to 8 meters. I don't need to convert any units. Every unit here was already in MKS units, so I'm good in here. After we enter all these values, the answer we're going to get for force, my board is too small, let me put it in here, will be 2.03 times 10 to 30 Newton. This is a very large force attracting Moon to the Earth and causing it to rotate around the Earth. So this is one example. I'm going to delete this, and we're going to go on talk about the gravitational force pulling us towards the center of Earth, which is our weights actually. So weight is a type of force. And let's talk about it. And it's actually gravitational attraction force. So under this gravitational force, we're going to have another section as, let me use red for the titles, it's not very visible. Weight and mass. Quite often people confuse weight with mass because in daily life we use them interchangeably. So we generally use mass, and what we are actually putting as number is weight. But so yeah, let's talk about them. What is mass and what is weight? Let's see, we have Earth in here, and there's a person standing on Earth. It was black. This person is pulled towards Earth with a force, which is why we are stuck with Earth, which is a very good thing. We need this gravitational force to be safe and live on Earth. So there is a force acting on the person by the Earth. Person is also pulling Earth towards itself or himself, and it's equal in opposite direction. But let's not talk about that yet anymore. We are interested in what is the force that is exerted on the person by the Earth, and this very force is the gravitational force is equal to weight of the person. So for weight, what we're going to use as a symbol is W. Let me write it first. So what is this equal to? If I call the mass of the Earth M Earth again, and mass of the person M, a small m only, F force in between the Earth and the person is equal to G M Earth, mass of the person divided by R squared. Let me put it here. This is the distance in between the person's center of gravity and the center of Earth. Actually, we ignore the person's center of gravity, which is very small. We generally take this distance R as R Earth, which is equal to radius of Earth. And this is the force exerted on the person. And this is equal to weight of the person. So what is the unit for weight? Newton, because it's a type of force. What is mass here is m, mass of the object. It's in kilogram. So how we feel the weight, actually, when we are using these scales to weigh something, apples, pears from store, actually what we're looking into is the weight as a force. And the unit should be Newton, but it's converted into mass again, so we can understand it. So we go by kilograms, grams, or pounds. Actually, what we're measuring is the pull by Earth, gravitational pull by Earth, which is force. So mass is the amount of matter an object has. And the weight is the gravitational attraction force on the object by the Earth, if the object is on Earth. If the object is on the Moon, there is a gravitational force by the Moon. And the weight, which is the gravitational attraction, for a person with the same matter, same mass, is different on Earth and different on the Moon. Now this weight is very simply solvable as m times g. And g we know is the gravitational acceleration. We've been using this already. And this weight mg is exactly equal to this in here, g m Earth, m mass of the object divided by r squared, which is equal to our Earth. So from now on, when we talk about weight, we don't have to go in all into this trouble. We just do m mass times gravitational acceleration, gives us the same result. If I enter these values in here, our Earth squared I'm putting now, so it's taking as like our Earth. And I write this in a better format, so I'm going to define my G actually. It's calculated, it's an anomaly, we don't have to recalculate it all the time. But let me see. So we have M in here, the mass of the object, same. And I'm putting in a different format to separate mass and all the rest. So I have left here G, Earth, divided by R squared, R Earth squared. So mg is equal to m times g m Earth divided by R squared, means that this is actually equal to gravitational acceleration. So how is the object pulled down by this gravitational acceleration? I don't have to recalculate it, it's already calculated, there's an accepted value for it, so I'm not going to go into this trouble when I am dealing with a weight. I'll just take the value, 9.8 meters per second squared. If I go into all this trouble, calculate the force exerted on objects by the Earth, I'll get the same answer as mg. So from now on, we're talking about weight of an object, we'll go by mg. And we will know, we're physicists, that it is equal to force exerted on the object by the Earth, gravitational force. Simplified, calculated, and given to us for our easiness. So that is what weight is and what mass is. Weight is equal to mass times the gravitational acceleration. Mass never changes, it's the amount of matter an object has, but weight changes. It depends on the gravitational acceleration. On the moon, G is smaller. Gravitational acceleration of the moon is about 1/6 of the gravitational acceleration of the Earth. So if we go to the moon, we'll be lighter and thinner. So this is weight. I'm going to delete this now. I have to. And I'm going to talk about one more thing. If we have a mass on Earth, let's say the object is in here, and if we take it, move to very far away, we call this position 1. Let's take this, move into the space very far away, considerable distance, not on Earth, not from a lower place to higher. It is also important, but very small difference there. Let's say I move this from 1 Earth to 5 Earth. So the weight here was mg of this object, but if I take it to very far away, mass is the same, weight will not be the same. Weight will be g prime, let's say, and g prime will be changing. G is equal to universal gravitational constant times m Earth divided by R Earth squared, but g prime will be universal gravitational constant m Earth divided by 5 R Earth squared, which is significantly decreased, maybe even 0, which is why astronauts in space do not feel gravitational force and they are floating in the air. This is a detail. If I want to draw a graph of how mass and weight changes as we go away from Earth, so let's see, this is distance and this is weight and mass. First let me show weight or mass easier with a blue color. No matter where I go, this is the center of Earth, let's say. Mass is the same, m, never changes. But for weight, it has a value at the center of Earth, or on the surface of Earth, sorry, surface. Center is more complicated. As we go far away, since it's dependent on our Earth squared, g is dependent on our Earth squared, mg will be decreasing. Inversely proportional to our square, so it will be decreasing in this format. And this will be decrease in weight as well, because weight is equal to mass times g. As g decreases, weight decreases. But mass stays constant. So this is the difference between mass and weight. What we are dealing with in Newton's laws, Newton's applications of Newton's laws is generally weight as a force and mass as mass. And mass is a scalar quantity, weight is a vector quantity. Let's solve an equation, a problem, to see why we don't feel any forces. If there's always forces in between two masses, why don't we feel it? Because it is very, very small and we don't feel it. Just like there's air drag, we walk through the air, it's exerting a force on us, but we don't feel it because it is very small, insignificant, and ignorable. So I have a question here. Calculating the force exerted on two masses by each other, gravitational force. So let me find it. I think this is example 2. We have two masses, M1, M2, regular masses, not Earth and Moon. And there's a distance between them as 1.2 meters. This is regular distance on Earth. M1 is equal to 12 kilogram. And M2 is equal to 25 kilogram. What is the gravitational force exerted on M1 by M2? Or what is the gravitational force in between these two objects, which are equal to each other? So I'm going to skip F1, F2 for now. It's F and it's equal to each other. I'm going to draw two forces. This is what M1 is exerted on M2, and this is what M2 is exerted on M1. And this F is equal to G M1 M2 divided by R squared. So 6.67 times 10 to minus 11 Newton meter squared divided by kilogram squared. 12 kilogram M1, 25 kilogram M2. 12 kilogram, let me put parentheses again, times 25 kilogram divided by distance squared. This is very bad. 1.2 meters squared. If I put all my units again in MKS units, my force will be in Newton. I'm not going to go into checking all the units. All I check is that they're all in MKS units, and I did that. Meters, kilograms, and seconds. And the answer is 1.4 times 10 to minus 8 Newton. Very, very small force. Now let's see what is the force exerted on these two objects by the Earth, which will be their weight, mg. So if I then look at the force by Earth on these objects, force by Earth, which is weight, gravitational force by Earth. So for M1, weight 1 will be M1g. M1 is 12 kilogram, and g is 9.8 meters per second squared. All MK students, my answer will be in Newton. And the answer for that is 12 times 9.8. Do I have it in here? Yes. 117.6 Newton. 117.6 Newton. See the difference? The Earth is exerted on this mass. Force is 117.6 Newton. Feltable force. But the force exerted on this object by a 25 kilogram object is 1.4 times 10 to minus 8 Newton. Ignorable, so we don't feel it. Is it there? Yes. This is that. Go ahead and find the force exerted on M2 by Earth, which is weight, M2 times G. Will be even larger. What I found is the 245 Newton feltable force. This is why we don't feel the gravitational force in between two small objects. But when we go to very large masses, that's the Earth the sun, the moon, then the force is feltable. The gravitational force is important when we go to large distances, small distance, large masses, because it's inversely proportional to distance and directly proportional to the masses. So this is gravitational force. Weight and mass are related to gravitational force. Now I'm passing this. The second force I'm going to talk about is normal force. This is a lot simpler. And we see it in questions. Let me put here in this corner. The first force was gravitational force. We talked about. And the second is normal force. Normal force is all. Doesn't matter. So the second force we're talking about is normal force. Normal force is the force exerted on an object by a surface. But it is the perpendicular force exerted on an object by a surface. So if there is an object standing on a surface, simple case, let's say it has a mass m, what is the force exerted on the surface by the mass? First of all, is mg, it's weight, right? Now we know that. Let's skip weight as well, we just call it mg. And we'll be pretty familiar with this. When we say a mass standing somewhere, there's mg there, towards the center of Earth, downward direction. This is the force exerted on the surface by the mass, and the force exerted on the mass by surface will be equal to this force, opposite in direction. Right? Which Newton's law is in there? Third law, action, reaction. There's an action on the surface, mg, there's a reaction force. And this reaction force is equal to normal force. Normal angle, as you know, is perpendicular to a 90-degree angle. This is why it is called normal force. It's perpendicular to the surface, always, and is equal to whatever perpendicular force is acting on the surface. Total perpendicular force is acting on the surface. Here is equal to mg. Now I'm showing magnitudes only. The directions are visible, obvious. Mg is downward and is in the opposite direction. Now it could get tricky sometimes. It's not always mg. For example, if I put here, let me call this example 1 and learn this by way of examples. If I put here a mass, example 2, still mg is still there. How about if I exert another force on this m? Let me start simple and call this F. What happens is, now we have two forces pushing down, right? I'm pushing with my hand, let's say. This is my object. I put it on a surface. There's mg. And if I extra push it with another force, this is adding up with mg. The surface now has two force effects on it, acting on it, and the reaction force will be equal in opposite direction and equal to the total force, total perpendicular force acting on the surface. So we still have mg here, plus F pushing down, then N will be upward direction, again perpendicular to the surface, and it will be equal in magnitude to F plus mg. It is working against all these action forces, action force, and reaction force. Now that could be many different situations. Let me say example 3. I put the mass on the surface. Let me put these here to clarify. Now I'm pushing down with a force that is with an angle horizontal. Let me call this angle alpha. This is again F, but now it's not perpendicular to the surface. It has an angle with horizontal axis. What's going to happen now? My normal force is interested in only perpendicular forces acting on the surface. And the reason is very obvious. If I divide this F into its components, we will have Fx and Fy. And if this is alpha as well. So cosine Fx is F cosine alpha. I'm not going to go into that. I assume and hope you are all comfortable with this now, and Fy is F sine alpha. As you can see, Fx is parallel to the surface, so it's only can only do is to push the mass to the right along horizontal, and it's not having any effect on the surface. What is pushing down on the surface is actually the perpendicular y component of F. So if I wanna carry this Fy in here, I'll understand it better. Vectors can always be carried as the same direction and magnitude to any position you want to be able to solve your problem easily. So that's what I'm doing here. Do I have to do it? No, but I'm doing to clarify it for you. I know this Fy is acting on this mass because my F is pushing here. So this Fy and Fx are actually in here. But I show them like this to help you understand the components better. So I carried Fy in here now. Is mg still there? Always. Now my total forces acting on the surface perpendicularly is Fy and mg. Then what my n will be is Fy plus mg. Opposite magnitude, equal in magnitude, opposite in direction. This is normal force. There are many other situations for normal force. For example, if I have an object, if I put this object in as I leave it, it will fall down because there's mg pulling it down, right? But if I put it here and push it with a force, what I'm doing now is sticking it to this wall with my force. There's an action exerted on the surface, which is the whiteboard by my arm, F, and there is a reaction force as normal force. And what kept this object in here is actual friction on the surface, and we'll get the friction right after this. Another nice force. So let's say example 4 in here. There's a wall, let's say. There's a mass. If I leave this mass in here without any force, it will be falling down. No surface can have large enough friction to keep it there. So I will have mg always in downward direction. If I leave it like this, is there any normal forces? No, zero. There is no force acting on the surface perpendicularly, and there is no normal forces. But if I push it with another extra force to the surface, F, my normal force now will be equal to F in opposite direction. N is equal to F. This is normal force. One more important example I have to give you before moving on away from normal force is, let me delete this first one. I don't know if you're writing down. I'm going to put notes, but my notes are not always exactly what I'm doing in class. Sometimes something comes to my mind and I tell it there. But you can go back watch the video if you like. Writing down notes would work better, so I suggest you to write down notes as you watch. It's up to you though. One more example that we quite often see is inclined surface. What happens there? What is normal force? And as we move on with next force, frictional force, what is frictional force there? So let me just show you the inclined surface. Oh, it's been some time. Okay. This is the 5th example. If we have an inclined surface, we put a mass there, and this alpha angle is important for us. We always have to know it. We put a mass in here. Let's find what is the normal force in this surface. In the beginning, when we were talking about vector components and choosing a coordinate system, I mentioned about this. Now we get to here. We are going to choose a coordinate system that is appropriate for us to find the components of our vector here, which is mg, force. Force is a vector. Again and again I tell you that, and I'll keep telling you that. So if there's no friction, let's say the surface is frictionless again. We didn't get there yet. The only force here is mg. This thing will be going down, but the force that is pulling it down is related to mg, not mg. It's the component of mg. So we have to find the component of this mg, which is a force and weight. Let's drop weight. Let's not go back there. We dropped it already. So the system we're going to choose will be the most convenient one for us. I had something to help me to draw a better straight line. So this will be my xy coordinate system whenever I have an inclined plane. This will be my y, and parallel to the inclined plane will be my x. Now along this inclined plane will be the motion. And if I choose my xy coordinate with this coordination, with this orientation, it will be easier for me. Now if you look at this, turn like that and look at it like this, you will see this is mg. If this is alpha, this is also alpha. Okay? And this mg has components along x and y. This is y, this is x. I am drawing perpendicular lines to y, and this will be the y component of mg. And this is equal to mg cosine alpha, because my alpha is touching the y now. And I draw another perpendicular line to x-axis. This is finished grade. And this is mg sine alpha. It seems the components are switched now, but they actually didn't switch. The angle we were looking so far were always the angle between x-axis, let me call this theta, x-axis. So now we have the angle easily foundable with the y-axis. If we have that, and then cosine sine switches, because if we have two angles, this is a trigonometric fact, that are completing each other with 90 degree, alpha theta. Alpha plus theta is 90. Then cosine alpha is equal to sine theta, and sine alpha is equal to cosine theta. So far when we were finding the components, always looked at the angle between x-axis and our force. Now we can easily find this angle, which happens to be in between y-axis and our force. So y component is mg cosine alpha, and x component is mg sine alpha. Due to this rule, these two are completing each other to 90 degree. Cosine alpha is equal to sine theta, and sine alpha is equal to cosine theta. So if I again replace with theta, it will be the same. My y component mg sine theta, angle in between x and the force, and this will be mg cosine theta. Know that, don't get confused, it's the same thing, only I'm looking at different angle. You can find this angle, get the theta, which is equal to 90 minus alpha, and always use this if you are getting confused. But it's not very hard to understand that we switch the angles now. Due to this rule, we can easily find y component mg cosine alpha and x component mg sine alpha. So this is what we're going to do in here if we have an object on inclined surface. Now I am leaving this in there so it's not to complicate it too much. So we have our coordinate system. We don't always have to draw this coordinate system. Only at the beginning I'm showing it to you to help you understand what we are doing here. But whenever we see an inclined surface from now on, and m is sitting on here, and we have this alpha, right away we'll be comfortable enough to go ahead and say, well, I have mg in here. Perpendicular to surface, I have mg cosine alpha. Parallel to surface, I have mg sine alpha. We will notice, we'll put these there right away, and now if I go ahead and think about the normal force, this is my surface, which is why I want to give you this example, and the normal force will be equal to the force that is pushing perpendicular to the surface and opposite in direction. And the force that is pushing on the surface perpendicularly is mg cosine alpha. And my normal force will be equal to mg cosine alpha. Hope this is clear enough. And now we'll move on to last two forces actually. Okay, 5 minutes should be enough to talk about last two forces. So this is normal force. Without deleting that, I'm going to go into third force, frictional force. Force of friction. Let me put it in here as well. So 3 frictional forces. We know if we want to push a table or a chair, let's say, on a floor, if there's a carpet in there, it's harder to push rather than if there is a smooth surface, or if there is an icy surface, it's very easy to push because the friction changes depending on the surface. So frictional force on a surface changes depending on if the object is stationary or moving. So we will be talking about static frictional force, static friction, let's say. If an object is stationary on a surface, and if there is a static frictional constant, mu s, if we want to pull or push this object, let's say we're trying to pull this object with a force, there will be a force pushing us backward against this force, and that is for frictional force. We're going to be using small f to clarify. It will be a static frictional force. Now, unless my force is larger or equal to Fs, the object will not move. If F is larger or equal to Fs, the object will move. Until the object moves, the effective frictional force is static frictional force. And what is this force is equal to? We know we have mg in here, and we have normal force, and in this case only equal to mg. It changes depending on case to cases. And the static frictional force, Fs, is always equal to n normal force times mu s, static frictional constant, the frictional coefficient. Now, unless again F is larger than static frictional force, the object will not move. If it's larger, the object will move. Okay. Once the object starts moving, is there still friction there? Yes. Our work becomes easier because after the object starts moving, we have another force in effect, which is kinetic frictional force. And the difference is not much actually, but there is a difference. If the object is moving, mu will change, the friction coefficient will change to kinetic frictional coefficient, and it is generally smaller than static. So we will be having a little bit less friction. Once we can get some object to move, you can imagine from life, I've seen this many times, when we are trying to push something, it's so heavy in the beginning, it's very hard to start moving. But after we started moving, it gets easier. We can continue moving because frictional force actually gets less. The frictional coefficient becomes smaller. So if the object is moving, let's put in here, if F is bigger, object will move. If F is smaller than Fs, object will not move. So if we have F, if it's the object is moving, F is bigger than or equal to F static. After moving, we don't consider static frictional force anymore. After moving or after motion, F kinetic is in effect. And it's calculated the same, only the frictional coefficient, kinetic frictional coefficient will be different. And it's generally smaller than static frictional coefficient. This is why our work becomes easier. We will still have a frictional force, but it will be kinetic frictional force. We still have mg in here, and n is equal to mg for this question only. And Fk is equal to mu k times n. I'm putting n, I'm not putting mg, because as we have learned in the previous part, n is dependent on the object. If there are other forces affecting the surface, whenever there are different perpendicular forces on the surface, n changes. As n changes, friction also changes. Which is why in here, if I put this, it falls down because frictional force is not large enough. There's no normal force actually. It's almost zero, right? Very little one. There's no normal force pushing it. We can say it's zero actually. Unless I push it down in here, give it a normal force, and this normal force will help gain a frictional force to keep it there against gravity. So this is frictional force. Coming back to here, for example, let me divide this part. If I have an object on a surface, on an inclined plane, and if, say, let's go into kinetic one. We won't be dealing with static frictional force too much. We'll be looking at motion generally. In some questions we might, but generally we'll be looking at motion. So kinetic frictional force coefficient mu k. And there's a friction in here. To find the frictional force acting on this object, this object will be trying to move down. And the frictional force will always be opposite to the direction the object is trying to move. If it's trying to move down in here, it will be opposite direction. If the object is trying to move to the right with a force, frictional force is opposite to it. If I try to push the object to the left, then the frictional force is again opposite to what direction I'm trying to move the object. So this object is trying to move down. Frictional force Fk will be against it. Is equal to mu k times n. And what is n in here? Mg cosine alpha. I'll be replacing n by mg cosine alpha. And find the frictional force. Okay? If I'm asked to find if this object moves or not, first of all I calculate the static frictional force to see what is the largest amount of friction it has. And then calculate mg sine theta, which is sine alpha, which is trying to pull the object down. If this mg sine alpha larger than the static frictional force, the object will move. Once it starts moving, I'm not interested in static frictional force anymore. I'll look at the kinetic frictional force. And the total force for the system, if it's moving, will be mg sine alpha minus frictional force, kinetic frictional force. We'll get into those, understand them better when we get into the applications of Newton's law. In the applications, we'll be using all these forces, kinetic, static, frictional forces. Not static very much, only in some questions I've said, if I'm asked to decide if the object moves or not, I'll look at the static frictional force first. But generally we'll be knowing if the object is moving, and then we'll be dealing with kinetic frictional force most of the time. And weight, quite often, gravitational attraction, gravitational force. And one last is the tension force in a rope if we are hanging something and so on. The last force, I'm going to quickly tell you, this is a little bit longer than previous lecture, but I hope you'll like it. Last force is the tension force. It's quite simple actually. Whenever there is a tension force along the same rope, the tension will be the same. That's the only detail we need to know about. And we'll be solving a lot of questions about all these forces, so we'll be comfortable with them hopefully until this section ends. These are again applications of Newton's laws is chapter 3 in your book, and Newtonian mechanics starts in chapter 2. So the fourth force that we will be interested in here is tension force. Force of tension or tension force. So if there's an object we're pulling, let's say, with a rope, with a force, there's a rope in here, and we hold it with a hand. Oh, I can't draw a hand, but let me try. The person is pulling it with a force F. The tension in the rope we generally will call T. It is equal to F in opposite direction, and along the same rope tension is always the same. If the rope is changing, we'll be looking at more complicated cases like pulleys and so on in the future. This is an important thing to know. If I have an object, for example, hanging from a wall, a bucket full of water, and there will be tension pulling this object up, tension force. If there's mg, for example, tension force should be equal to mg so it will not break. We'll get to that later on, so don't worry about it too much. If I hang this object with two ropes, let me see if I can draw something like that. Let's say I have a pulley in here. We'll be doing detailed questions about pulleys and so on, so don't worry right now, just to show you. And I put a rope, in this case, two sides. This will be helping strengthen my pull because along the same rope I will have tension same. So I'll have a tension here on this side pulling up, let me call it T, and on this side as well pulling up. Now my mg is divided into two forces, and it's more strong now. It's safer to hang my pail in this way. Along the same rope again, the tension is the same. And the direction of tension is two ways. Always if I'm looking at this position, it's pulling up. If I look up in here, this rope is actually in here pulling down. So we'll be applying those to solve our questions. In these applications, which will be equilibrium and equilibrium, and next lecture I'll be talking about that. So I hope this will be helpful for you. This was just to introduce you to different forces. Are there any other forces? Of course, there are electric forces, magnetic forces, there are nuclear forces, but in this course we're not interested in them. This is all we're interested in. Gravitational force, which will generally weight, will be dealing with mg, normal force, perpendicular force to any surface, equal to normal force opposite direction. Frictional forces always against the motion of the object, and tension force along the rope. See you in the class.